All right, section 1.8. This is the last of the sections in chapter 1. Higher order derivatives. So our objectives are to find derivatives of higher order, given a formula for distance, find velocity, and acceleration. So some of our vocabulary, the nth derivative and position velocity and acceleration. Those are actually couple of the better applications, easier applications for us to talk about. Okay, higher order derivatives, again, might look a little intimidating, not really a difficult concept in the fact that a higher order derivative literally just means we are taking a derivative of a derivative. So if a derivative is a rate of change, it's how that rate of change is changing. That's what we're really talking about here. In general mathematics, it's literally just a derivative of a derivative. So if you follow the example, if we start off with the original function x to the fifth minus 3x to the fourth plus x, and you take its derivative, you get f prime here, which is this one, 5x to the fourth minus 12x cubed plus 1. Then if you were to take the derivative of that one, notice the notation here. It's got two prime symbols here. It just means the second derivative. We say f double prime. And then you would just take the derivative of the previous thing that you just had. So we take the derivative of 5x to the fourth, it's 20x cubed. Take the derivative of negative 12x cubed, and you get negative 36x squared. The derivative of 1 is 0, so it's gone. And then likewise, if I wanted to take the derivative of the second derivative, you now see that we have three prime symbols. It's called f triple prime. That would be 60x squared minus 72. These, as far as I know, I don't think that these are correct notations, as a matter of fact. I've never seen this before. So if this is actually in your book, maybe it's something that I'm unfamiliar with. I do not use those notations. I think that the prime symbols technically stop. So I'm going to rewrite this. Usually after the third prime symbol, we just start putting numbers up there, but you can't write that because that looks like f to the fourth power. So what we do to indicate that it's a derivative is we put it in parentheses. That would indicate a fourth derivative. A fifth derivative would just be f with a 5 in parentheses, and then a sixth derivative, and so on. So pretty much after we get past the third tick mark or the third like apostrophe, we start putting numbers in parentheses to indicate the derivatives. Notice what happens once you get to the sixth derivative, because once you get to the fifth derivative, it's a 120, which is a constant. Then you take the sixth derivative, it's 0. Every derivative thereafter, the seventh, eighth, ninth, 10th, every time you take the derivative of 0, again, it's just 0. So you take enough derivatives of a polynomial function, it's eventually going to what we call terminate to the fact that it's going to always be 0. Okay. So it says here you're wondering about notation. Wouldn't it be tedious to figure out that many derivatives if the 11th derivative or 12th derivative? For that reason, we developed an easier notation for higher order derivatives. Maybe I just didn't look further down the page here. Yes, there it is. The fourth derivative. So we stopped using the prime symbols. I just didn't look far enough down my page here. But there is the parentheses notation. The nth derivative just means however many derivatives we're going, it just means we don't have a specific number in there. Any derivative that we want to plug in here for n, that's the derivative you're looking for. So that's what an nth derivative is. So if n is 12, then I'm looking for the 12th derivative. If n is 37, I am looking for the 37th derivative. So it's just a general notation for that. Want to point out some of the other notation here. The Leibniz notation is a little strange when you look at it. It's telling you, the first one here is our dy over dx notation. That one we've seen. When you take the second derivative, it's really the derivative of dy over dx, which notationally we write like this, right here. It's d squared y over dx squared, and that's because technically that y can be pulled off to the side. Otherwise, you would have a square on top and bottom because it indicates a second derivative. Third derivative, same thing. Fourth derivative, nth derivative. Technically, we could take this y And we could pull it off to the side just to put it right there, not in the bottom, just off to the side. So that would be the third derivative. You could take that y, pull it off to the side. But that's why the 4 comes in between the d and the y on the top, but after the dx on the bottom, because it's really 4 dx's. Probably should actually technically have that dx in parentheses down there on the bottom, but we don't ever write it like that. So that's just notation. If you see those, that's what they mean. So again, pay attention to the notation there. Take the derivative of y however many times. All right, so let's go ahead and do a couple of practice problems here. So if I have the function y equals 1 over x, we want to find d squared y over dx squared, which is the second derivative. Well, in order to get to the second derivative, we have to take the first derivative. So let's find the first derivative. Let's find dy dx. Well, 1 over x is the same thing as x to the negative 1 power. So we're going to use the power rule, and we're going to bring down the negative 1. And then we're going to reduce the power by 1, so that's now negative 2. All right, now if I want to take the second derivative, I am taking the derivative of the derivative. So that's going to be d squared y over dx squared, which is just the derivative of the step above. I'll bring the negative 2 out to the front and multiply it. We get positive 2. And then we reduce the power by 1, and we get negative 3. So that's the second derivative. And if we wanted to rewrite that, that would be the same thing as 2 over x cubed. Okay, exactly the same thing. All right, let's go ahead and take example 2 and find its first and second derivative. So we are looking for y prime and y double prime. We haven't really used this notation, but it's the same thing as dy dx and d squared y over dx squared. It's the same thing as f prime and f double prime. It's just y prime instead. So let's go ahead and use that jeepers notation. So y prime is the derivative of y. This is going to be a chain rule, because I have a whole thing on the inside raised to the 20th power. I do not want to expand that thing out by multiplying that thing 20 times. So we're going to use the chain rule. We'll bring the 20 out to the front, keep the inside the same, reduce the power by 1. Now using the chain rule, we must multiply by the derivative of what's inside the parentheses, or our composite function. The derivative of that is 2x plus 10. Now I want to find the second derivative. This is kind of why we practice the stuff that we practiced in the last section. The 20, it really could be multiplied. You know what? Let's probably do that. The 20 could be multiplied into here just to make this a little bit easier. So on the previous step, because I know what's coming, I'm going to multiply that in. I'm going to leave the x squared plus 10x to the 19th power as it is. But then I'm going to distribute that 20 into the second parentheses. So we're going to get, let's see, what is that? 40x, 10 times 20 is 200. That's just going to make it a little bit easier to do our second derivative. So it is going to be a product rule, but within that product rule, this piece right here is going to be a chain rule. So let's do that. The derivative of the first term, which is the one I just underlined, is going to be a chain rule. 19, keep the inside the same, reduce the power by 1, complete the chain rule, so that's the derivative of the inside, which is 2x plus 10. That's the derivative of the first, times the second one, which is, let's do that in red, this one, times the second one, which is 40x plus 200, plus the derivative of the second one. That's much easier. The derivative of 40x plus 200 is just 40, times the first one, which is x squared plus 10x to the 19th power. Again, we're not going to simplify that one any further. We don't need to. It just said to find the second derivative, and we have done that. So Why would we need to use all this stuff? Well, one of the better applications, or most common applications, is in some basic physics. Position, velocity, and acceleration, and how they relate to each other. So the position of a function just tells you where it is. If you were to take the change of a position, if you were to figure out how a position of something is changing, you're actually finding its velocity. So if you were to say you start at one place and you finish at another place, and it took you a certain amount of time to get there, you've done some kind of a velocity to get from one place to the other. And that's the rate of change of the object. That's called its velocity. And then if you were to actually take the rate of change of the velocity, you're finding its acceleration. Acceleration is how the velocity is changing. Is the velocity getting faster? Is it getting slower? Is it moving in a specific direction? Is it, what's the acceleration doing? How is the velocity changing? So if I were to take, oh, by the way, and for whatever reason, position is labeled as S of t. I actually still do not know why they use S. I am sure that there is some kind of foreign language derivation that uses that for S in this case. The V and the A make perfect sense to me because that's velocity and acceleration. S is position, so we just have to get used to that. But S prime, which is the derivative of S, we just said is velocity. That's this one. And then the derivative of velocity, or V prime, is acceleration. But acceleration, because V prime is the derivative of S prime, is also S double prime. So S double prime is acceleration. So the second derivative of position is acceleration. Again, higher order derivative. All right. So one of the ideas is you can think of these in terms of taking a car trip on a number line. S of t is a mile marker on the highway. This gives you the absolute position of the car. So if you're driving down the highway and you see mile marker 124, you know that's where you are at that specific point in time. V of t is the speedometer reading. So as you look down at your speedometer, as you pass mile marker 124, it says whatever it says, 57 miles per hour. That is your instantaneous velocity, instantaneous rate of change at the moment in time that you're looking at the mile marker. A negative velocity, this is important. Negative velocities do exist. It does not mean you actually have a negative velocity. It just indicates that you're moving in a backwards motion from whichever direction you would call forward. So you're going in reverse. And then A of t is the speed at which the car is speeding up or slowing down. So is it a positive acceleration or is it a negative acceleration? Deceleration technically is not a word, but you can accelerate in a negative direction. Basically, it means that your acceleration is working in opposite direction as your velocity. The best way I can say that is if your car is moving this way and then you hit the brake, your acceleration is moving this way at the same time that your velocity was moving to the right, which is what slows the vehicle down to a stop. Okay, so velocity and acceleration working in opposite directions will slow something down. Velocity and acceleration in the same direction will actually speed the object up. Okay, that's kind of an important thing to know as well. All right, so let's look at some more examples. Example 3, when an object is dropped, the distance it calls in t seconds, assuming negligible air resistance, is given by. So this right here, S of t, once again, that is a position function. It's telling us that once we drop this object, the position is given by 4.905 t squared, where S of t is in meters. So whatever this thing is dropping, we're doing it in meters. If a stone is dropped off a cliff, find each of the following, assuming that air resistance is negligible. We keep saying that because air resistance can give you friction, which can affect the velocity and the acceleration of an object. We're just assuming that this is not something that we're worrying about. So how far has the stone traveled in 5 seconds after being dropped? So if we want to know how far the stone has traveled, basically we want to know where it was when it started, where is it 5 seconds, and then figure out how far the distance was that it changed. So what we really want is we want S of 5, and we want S of 0. Well, S of 0 is easy, because if I plug 0 in for t, I'm going to get 0. So we're going to call whatever this thing is place 0. If I want to figure out what S of 5 is, we're going to have to plug that into a calculator. So 4.905 times 5 squared, which is 25, is going to give us 122.625 meters. So if I take the difference in those two, well, obviously 122.625 minus 0 is just 122.625. This thing moved in those 5 seconds 122.625 meters. Now we want to know how fast the object was traveling at the 5-second mark when it was after it was dropped. Well, that's an instantaneous rate of change at 5 seconds. So what I am looking for is the velocity. We want to know how fast it was traveling, and we know that the velocity of an object is the first derivative of position. So let's go ahead and take the derivative. Well, if I take 4.905 and multiply that by 2, we're going to get 9.81 t, reduce the power by 1. But we want to know what this is at 5 seconds. So the velocity at 5 seconds is 9.81 times 5, which is 49.05. Velocity is how something is changing over time. So this is going to be, let's see, we're talking about meters over, does it say, are we in second? Yeah, we're in seconds, so meters per second. Velocity is in meters per second. And then we want to find out the acceleration of this thing at, again, the same time 5. Well, acceleration is the first derivative of velocity. It's how the velocity is changing, which is also the second derivative of position. Much easier just to take the first derivative of velocity since we found that above. And the first derivative of 9.81 t is just going to be 9.81. So the neat thing about this one is 9.81, there's no variable left there. So the acceleration at time 5 is 9.81. The acceleration at time 10 would be 9.81. The acceleration at time 2 would be 9.81. It doesn't change. Let's see. So what are the units here? So acceleration is how velocity is changing over time. Well, velocity was meters per second. Or another way to write that is meters per second squared. And that is your acceleration. Okay? Example number 4. Let's look at this chart. Kimberly leaves her home. We're going to call that distance 0 for a 2-hour bicycle ride. The graph of her distance traveled with respect to time is shown below. Important note, much like a distance tracker on a Fitbit, this graph represents the total distance Kimberly has traveled, not necessarily how far she is from home. That's a different thing. That's actually called displacement when you figure out how far you are actually from where you started. This is the total distance she traveled. So if she took 15 steps from her house and then came back to her house and then 15 steps out and then 15 steps back and then 15 steps out, it's going to track the total number of steps, even if she ends up back at her porch, which would say that she hasn't gone anywhere in displacement because she ends up at the same place. So this is a total distance tracker. So let's see. Find the interval in which Kimberly is traveling at a constant velocity. So if she's traveling at a constant velocity, let's see here. Whoops. Sorry about that. Kimberly is traveling at a constant velocity. So the graph is in distance, let's see, miles per hour. Okay, it's actually kind of hard to see from this graph, but what we're looking for basically are line segments. We are looking for things which are linear, because if you've got a linear piece, that means that you're traveling at a constant velocity, whether the velocity is positive or it's zero or it's negative. We have to take a look at this. So let's see if we can find these places. So it looks like right here there is a constant velocity, because according to this, the distance is not going up or down, which means the distance is not changing, which means that the constant velocity there is zero. So one of our intervals looks like it's going to be 0.4 to 0.6. Okay. Now the next one's a little bit more challenging. It looks like from 0.6 to 0.8, there's a little bit of a bend in that curve, so that's not constant. However, it looks like from 0.8 to 0.1, that looks linear. That looks constant to me. That means that the velocity is increasing, no, excuse me, that the position is increasing at a constant rate. So the slope of that line right there would be constant. Looks like it would probably be over, like, say 5 over 0.2 or something like that. But it definitely looks like we've got a constant velocity there, and that's going to be from 0.8 to 1. Let's see, where else would we have a linear function? From 1 to 1.2, it's curving, but from 1.2, it looks like to 1.5, that looks horizontal, so that's constant, that's linear. So 1.2 to 1.5, and boy, it's really hard to tell. I think 1.6 to 1.8 is also linear. I don't think that that's curving. Could be guessing here. But anyway, what you're looking for are linear pieces there. All right, so when is this thing speeding up? Well, that means that the rate of change of the velocity is actually increasing. So what you're looking for is kind of an upward bend to this thing, because you want the velocity, which is already going up, to be bending upwards. So I think we're talking about from, looks like from 0 to 0.2. Oops, 0 to 0.2, that's bending upwards. Okay, it looks like from 0.2 to 0.3, I don't know if that was a linear piece or not. As a matter of fact, I think maybe it is. Let's go back and add this as a linear piece. So we'll say 0.2 to 0.3 is another one where it was constant. For it to be speeding up again, it has to be bending up. So I think we've got another piece bending up right here. So 0.6 to 0.8. And then it looks like from 1.5 to 1.6. 1.5 to 1.6, also speeding up. And then where would it be decelerating or slowing down? Well, that would be a downward bend. So something like this. Because the velocity itself is still positive velocity, but you can see how it's bending down, meaning that the velocity is actually slowing down there. So I think we're going to go from 0.3 to 0.4. That's one interval. Looks like it's also bending down from 1 to 1.2. And then it looks like it's bending down here at the end from 1.8 to 2. I think those are all the intervals there, so I think we've gotten them all. All right. All right, last example. Example 5. This was an example that we did back in 1.7. We're just going to continue it. In which the new smartwatch was placed on the market. The function that was given by the one that's there, n of t, represented the total number of smartwatches sold after t weeks. Its derivative is this one right here. Now this is a simplified version of our derivative. We did not go far enough to simplify that, but that's what it is. So now it wants us to calculate the second derivative and interpret those results. at the same 2 times. So let's go ahead and find the second derivative. Well, the second derivative is the derivative of the first derivative. So once again, this is going to be a quotient rule. Within the quotient rule on the bottom, we have to do the chain rule. So the derivative of the top is 500,000 times the bottom, exactly like it is, minus the derivative of the bottom now is our chain rule. We'll bring the 3 out to the front. 2t plus 1. Reduce the power by 1. Don't forget now to multiply by the derivative of the inside of that parentheses, which is just 2. That's the derivative of the bottom. Now we have to times it by the top. And then all that divided by the denominator squared. If you square something which is cubed, then that becomes to the 6th power. All right, so now let's figure out what n double prime, that should be a double prime, looks like a triple prime there, n double prime of 52, which is basically 1 year, and n double prime of, my pen keeps dragging and makes it look like those are triple primes, and n double prime of 208, which is 4 years. All right, so let's plug those into the calculator, and we're going to see what we get. So at 52, if I plug that in, I'm getting negative 0.0, no, sorry, I can't read my calculator, negative 0.85. And if we plug in 208, we're going to get negative 0.01. Don't really need to round that any further, I don't think. So what does all that mean? Well, this is the second derivative. This is the rate of change of the rate of change. So the first one was, the first derivative was the how the number of watches sold was changing. Well, now this is how is the rate of watches sold changing. So we're talking about the number of watches sold here. So we're going to call that, I guess, what did we call the number of watches sold here? I guess just the number of watches sold. Okay, so it's watches sold. Watches sold per week, or per week squared. So again, watches sold per week squared. So it looks like the number of watches sold at that given time at 1 year is the rate of change is actually decreasing at the rate of negative 0.85, and at 4 years, which is 208 weeks, it's the rate of change of the watches sold is decreasing at a rate of, was actually changing at a rate of negative 0.01, or it's decreasing at 0.01 watches sold per week squared. That's the interpretation. All right, that is plenty enough for 1.8, a very long video. I apologize for the length of this one, probably one of the longer ones we've had. I don't think it's going to be very difficult, though. Higher order derivatives are not horrible unless you're combining them with a whole bunch of other things, which can happen, so you've got to keep all your rules straight. All right, good luck.